Hello everyone, and welcome to PostGIS Day 2025 Hexagonal Thinking Talk. It's great to be here. Today I want to talk to you about hexagonal thinking, specifically how we can manage massive, complex climate datasets using the power of PostGIS combined with the H3 grid system. We are going to look at this through 6 specific angles or sites that we discovered while building our platform, drought.uk. We will explore how we moved from traditional spatial management to a hexagonal approach to unlock the speed and scalability. Okay, first, a little bit about my background, so you know where I'm coming from. I'm a geospatial developer and entrepreneur with about 22 years of expertise in the field. For the last decade, I have pivoted my focus almost exclusively to the climate change related projects. You might have seen my work on globaldroughtmap.com, and currently I'm deeply involved in the development of drought.uk. In building these systems, I realized that standard JS approaches weren't enough for the sheer volume of the environmental data we are seeing. And what about the challenge? The core issue we face today is that a call to tsunami, climate data to tsunami. Why this is to tsunami is worse than a normal big data. It is not just big, it's big and spatial. Spatial, temporal, multi-resolution, multi-resource is equals to exponential complexity. For example, a single Sentinel-2 tile is about 800 megabytes for 13 bands. Area 5 climate reanalysis is 35 terabytes for the full data set if you store raw hourly fields. And for NDVI and AFR time series, thousands of scenes per region per year. Most systems can handle big tables, but climate data is big tables plus expensive operations, reprojection, resampling, interpolation, raster clipping, spatial joins on large extents, temporal aggregation, monthly, yearly, and etc. Traditional database collapse under this load unless you build a very smart structure. Why classical JS fails here? Classical JS stacks like ArcGIS, QGIS, GDAL-based tools can handle rasters, but not easily at national or continental scale, not optimized for repeated queries over millions of pixels. Often batch-oriented, not query-oriented. PostGIS tries, but working directly with raw pixels, real rasters, is too heavy. And station data. The third one, station data, adds a totally different dimension. Climate stations are unevenly distributed, biased towards populated zones, often sparse or missing in rural areas. Come with a metadata, elevation, sensor type that must be harmonized. You need spatial interpolation, IDV, kriging, splines to create a gridded products. Mixing rasters plus points and polygons is very hard problem to solve. And the real question in the slides raises, how do we unify? This is where the entire talk is going. You pose the question, how do we unify, query, or analyze the disparate heavy data at scale without the database grinding to a halt? The audience will immediately think how you tile it, or do you tile it? Do you downscale it? Do you store raw rasters? Do you pre-process into cubes? This sets the perfect foundation for introducing H3 later. The unifying unit, the scalable spatial index, and PostGIS as the engine. Before starting, I just want to mention about the tech stack. To solve this, we settled on a specific high-performance tech stack. At foundation, as you expected, we have PostgreSQL and PostGIS. This is the bedrock of our spatial data storage. However, the secret weapon or ingredient is the H3 Uber's hexagonal hierarchical spatial index. This allows us to discretize the word into manageable cells. We utilize DuckDB for high-performance OLAP querying when we need to crunch the numbers, and we wrap the whole architecture in the Node.js to serve the API. Okay, let's walk through the 6 sites as I promised to Paul, just 6, no less or more, of how this stack works. Okay, the side 1 is the unified management for complex data. Angle 1 or side 1 is the unified management. One of the biggest challenges with climate data is that every dataset speaks in different language. You have a raster for temperature, a CSV for soil moisture, polygons for catchments, and point-based station networks for rainfall. Each comes with its own projection, spatial resolution, and temporal structure. What we do with H3 inside PostGIS is translate all of these formats into single, consistent spatial index. Rasters are sampled or aggregated into H3 cells. Vector points are snapped to their nearest H3 hexagon, and polygons are dissolved into hexagons they intersect. Once that happens, everything becomes simple. We have a table structure like H3 index, date, value, and data type. It no longer matters whether the original dataset was a GeoTIFF, a shapefile, or CSV. This normalization means PostGIS is no longer dealing with 5 incompatible spatial models. It's managing one unified grid, which allows joins, overlays, and comparison to become extremely fast and clean, all based on a single column of H3 indices. And next site is the powerful data aggregation. Climate data, by its nature, is noisy. We rarely know or need to know the NDVI or the SPI value for every single pixel. What we actually care about is the trend over a region, a catchment, or an administrative boundary. This is where the hierarchical structure of H3 becomes incredibly valuable. Because every hexagon has a parent at a coarser resolution, we can take high resolution drought indicators, SPI, SPEI, NDVI, soil moisture anomalies, etc., and roll them up the hierarchy with a simple SQL group by on the parent H3 cell. Suddenly, regional drought severity, monthly summaries, or long-term trends can be computed in milliseconds directly inside PostGIS. Instead of running expensive raster-based zonal statistics, clipping, reprojecting, resampling, we are aggregating clean, pre-indexed values. This turns what used to be a heavy JS workflow into a lightweight SQL query. Now let's come to site 3, scalable spatial queries. The third site is, as PostGIS users, we know all geometric intersections, ST intersects, ST within, ST union, are among the most computationally expensive operations you can run, especially when you are working with large detailed polygons or high-resolution rasters. When we shift to hexagonal thinking, we stop doing geometric math at runtime and start doing integer math. Every H3 cell is represented by a unique 64-bit integer or a text identifier. So instead of intersecting two geometries, we are simply comparing two integers, and that means our queries can write entirely on B3 index. If you want to know the drought status of a specific region, you don't need to clip a raster, dissolve a polygon, or run zonal statistics. I just fetched a list of H3 indices that fall inside the region and perform a straightforward lookup. This transformation, what used to be a heavy spatial operation, into a lightweight database query. And because integers scale linearly, these lookups remain fast when you are working with billions of rows. No geometry processing, no complex spatial joins, just pure scalable indexing. And site 4. This is hierarchical or multi-resolution analysis. Drought impacts occur at very different scales. A local farmer needs to understand soil moisture conditions within a few kilometers. A regional water authority cares about river basin trends. The national government wants to aggregate a picture of countrywide drought exposure. With PostGIS and H3, we can store climate indicators at finest practical resolution, for example, resolution 6, 7, where each hex might represent a few hundred meters to a few kilometers. What makes H3 so powerful is that parent-child relationships between resolutions are deterministic and reversible. Every resolution 7 hex has a clear parent at resolution 6, 5, and all the way up to resolution 1. This means we can query a single dataset at multiple scales simply applying H3 cell to parent in SQL. Need a basin level roll up to resolution 5. Need a resolution snapshot, roll up to resolution 3. This creates what I call a zoom stack for climate analytics. A database automatically provides an appropriate level of detailing depending on the user's viewing context, all without duplicating or pre-computing multiple datasets. In other words, we get multi-scale analysis with one unified H3 index table, and the transition between scales are seamless. Sorry, forget about switching the slides. Okay, the next one is Site 5, improved visualization. Most of us are used to viewing climate data as blocky raster pixels. The problem is that pixels, especially in WebMarketer, distort size dramatically as you move towards the poles. This makes spatial comparison misleading. Hexagon solves this elegantly. Each H3 cell has a consistent shape and consistent distance to its neighbors, which makes them statistically superior for modeling continuous natural phenomena like rainfall or drought intensity. When we render climate indicators on the front end using an H3 grid, the patterns appear more natural, more uniform, and much easier to interpret. Instead of rigid square blocks, the hexagonal layout reveals smoother transition and clearer flows across the landscape. In short, hexagons aren't just visually appealing, they communicate climate patterns more truthfully. And we came to last sites, bringing data to actionable insights. This is the really heart of the entire architecture. We are not building a spatial database because it's elegant. We are not aggregating SPI or NDVI into hexagons because it looks good on the map. We are doing this because stakeholders, from farmers to water regulators to national governments, need to answer the "so what" questions. By combining H3 indexed climate datasets with H3 indexed demographic or land use datasets in PostGIS, we turn scientific observations into real-world meaning. For example, we can instantly intersect drought hexagons with population hexagons to compute drought exposure. How many people live inside the area currently experiencing SPI index below minus 1.5? How many crops or hectares of agriculture fall into extreme dryness? How many critical facilities, hospitals, schools, reservoirs are in high-risk zones? These questions used to require complex GIS workflows, clipping rasters, running zonal statistic, reprojecting layers, and then trying to combine incompatible datasets. Now it's simple a join on H3 index. Because everything is aligned to the same hexagonal grid, the analysis becomes transparent, repeatable, and fast. This is what makes the gap between raw scientific data, which often just looks a binary drought mask, and the actionable insights that the policymakers, councils, and planners need to make decisions. In short, H3 gives us a shared spatial language, and PostGIS turns that language into intelligence. And what about the roadmap of or a life cycle of a data? The first we ingest, we load the satellite data, NDVI station data, calculate. Then we process it, clean, validate, store in PostGIS table. Then we aggregate them, snap to all points to H3 resolution 7 cells. And then we use it in our analysis and visualize it eventually. So H3 based map. Now, I just want to make a short demo on the drought.uk. Okay, this is the main map. By the way, there isn't any JS servers behind, just the Node.js. No geo server, map server, ArcGIS server is just the data, and hexagons are created on the fly. You can change to risk index, exposure index, rainfall, or you can just move between the time series. It's just super fast. Okay, what about the future? To wrap up, this combination represents the future of environmental data management. PostGIS provides us with the robust, industrial-strength spatial foundation we trust. H3 provides the universal high-performance indexing key. Together, they create a scalable system capable of turning massive, chaotic climate datasets into actionable intelligence we urgently need to combat climate change. Thank you very much for your time. I invite you to visit drought.uk to see some of these concepts in production. If you have any questions about the implementation or the stack, please reach out to me at the email listed here. I'm happy to take any questions now. Back to you, Paul.